Well, good morning. Glad you're here. And and I appreciate the fact that you are willing to listen actively, take notes, and think about things. It's a great thing to do. Those of you that are thinking about the systems that you deploy systems that you deploy to succeed, right? Keep thinking about that. To find What do you do to find just the success? And sometimes you got to try a system for a while, right, before you start to see the benefits. So as you're doing things, keep track of what you're doing and think about, well, what effect is this having on my outcomes? And then describe for yourself the process that you think you need to go through. And it's going to be an individual thing, but certainly there are elements that many of us share. So today's title is How Can a Graph Show the Solution? Making Connections, Systems, Solutions, and Graphs. So you've seen me use Desmos several times. Even yesterday I use it. So a lot of times I like to go to that table slash graph visual. It helps me understand a lot of things that are happening with the algebra. And we want to pull some of those things out. We're going to continue to work with this idea of elimination, and we're going to look at some systems that are kind of unique. These are not the typical systems you have, but we need to be aware that these things can happen. So number 101, this is the first item that we have, and this is at 1 minute and 53 seconds. The first item is a new elimination challenge. Carefully examine this system. Unfortunately, we're not sitting in teams, but if you want, you could pause the video and chat with someone and talk about things that you could do to solve this particular system. And I'm going to call out what I think is the technique I'm going to use. So when looking at this system, it's not the case that I'm going to be able to multiply one of the equations by -1 to get terms that are opposite to eliminate either x or y. And in fact, I'm not going to be able to multiply one of them by just a single value to get that situation. I believe I'm going to have to multiply both of these equations by something if I want to be able to solve the system. And that's not terrible. In fact, I probably am going to eliminate the y. And what I'm looking at is I can see that my first equation has the term plus 3y, and the second equation has the term minus 4y. So what I might do is I could set out to multiply this top equation by the number 4. And if I multiply the bottom equation by the number +3, it'll create a situation where the top equation is going to have a coefficient of 12y, or it'll have a 12y term, and the other one will have a term that's a -12y. And those will be opposites, so when I combine those equations, they'll go away. So let's set out and use that as our technique. If I rewrite this first equation, again multiplying every term by 4, it's going to become 16x plus 12y, and that will equal the number 40. And I'm just visually looking here. 4 times 4 is 16, 12, and 40. The bottom equation is going to become 3 times 9 is 27x minus 12y, and then it will equal 3. So now we're in a great situation where if I'm essentially adding 3 to both sides of the top equation. On the one side, I'm going to get 43 right on the right hand side. On the left hand side, I'm not actually going to add 3. I'm going to add something that's equivalent to 3. And according to the second equation, 27x minus 12y is equivalent to 3. So when I combine the 12y with the -12y, those cancel. So I have the 16 and 27. And when I combine those, I get 43. So I'm going to get, that's interesting, 43x equals 43. Therefore, x is the number 1. Now I can go back to either one of my original equations. I'll pick the first. And 4 times what x is plus 3 times y equals 10. So I'm going to place the value of x that I found, which was 1, into this equation. That's going to give me 4 plus 3y is 10. 3y is 6. Y is 2. So I believe my solution is the ordered pair 1, comma 2. And if I compare that, or if I plug that into the top equation, that's just going to give me, let's see, x was 1, that's going to give me 4 plus 6, which is 10. So it checks in the top equation. And for the bottom equation, it's going to give me 9 minus 8. 9 minus 8 is 1. So I can see that this is a nice job of solving this system. So this is a little bit of extension from yesterday. Sometimes if you want to solve a system using elimination, it's not enough to just multiply one of the equations by -1. Sometimes it's not enough to just multiply one of the equations. You might have to multiply both of the equations by something in order to get one of the terms to eliminate. All right, our second item starting at 629, and it says, the great Bob Ross says, and I've heard him say this during shows, you'll find the more you practice anything, the easier it gets. If there is a secret, it's practice. It's practice. Boy, that applies to a lot of things. A lot of things. So, the reason why I have that image is because this is about paint and painting. The art club at school is painting a mural using their school colors. Blue paint comes in a 5-ounce container costing $2 per container. The containers of silver paint hold 2 ounces and cost $3 per container. The art club spent $56 and bought a total of 74 ounces of paint. How many containers of blue paint and how many containers of silver paint did the art club buy? So when I read that and I hear it, I think, okay, there's 2 equations there. One is going to capture the number of ounces of paint, and the other one's going to capture the cost of the paints. And I need to define some variables, so let's start with that. And for my let statement, I'm going to probably use the variable b first. So I'm going to say let b equal the number of containers of blue paint. And the other one is silver, so let s equal the number of containers of the silver paint. Yeah. And the containers both cost a different amount each, and they hold different amounts of paint. So let's write the equation first of all for the total ounces of paint. Those blue containers each had 5 ounces, so I can say, hey, 5 ounces for every single blue container, plus the silver containers, they each held 2 ounces, so 2 ounces for each of the silver containers, and the total ounces of paint was 74 ounces. So this one's tracking the ounces of paint. Let's see, the other equation is for dollars. The blue containers cost $2 each, so $2 for every blue container, plus the silver paint costs $3 per container, so $3 for every single one of the S's, and that equals $56. So we can kind of see that what happened with our system above is happening here, right? I can't just simply multiply one of the equations by a -1 or one of the equations just by a number, it's going to take manipulating both of the equations to have elimination happen. I could eliminate the b's first. I could also eliminate the s's first, and to be honest, it's completely arbitrary. I probably will select to eliminate the s's because I'll get to use slightly smaller numbers if I do that. So I'm going to multiply this top equation by 3, and I'm going to multiply the bottom equation by, I'm going to pick -2. So if I pick the 3 and the -2, what will happen is this top coefficient for s will be 6 times s, and the bottom one will be -6s. So those will be perfectly opposites. So let's go ahead and write both of those. This top equation is going to become, let's see, 15b plus 6 times s, and that's going to equal 74 times 3, which is 222. And for the second equation, we're going to have -4b minus 6s, and that's going to equal 56 times 2, which is -112, -112. Okay, so when I add the equal things from the second equation to each side of the equal things from the first equation, over on the right hand side I have 222, and I'm going to combine that with -112, and I'm going to get just the number 110. My s's are going to be gone, right? So 6 times s plus -6 times s is 0. And I have 15 minus 4, which is going to be 11, positive 11b. So then 110 divided by the 11 tells me that there were exactly 10 containers of blue paint that were purchased. So b is 10. Now I need to figure out what s is, and I'll just use the top equation. So I'll just go 5 times whatever b is plus twice s equals 74. We found that b was 10, so we're looking at 50 plus 2s equals 74. And if I take the 74 and take away 50 from both sides of that equation, I'm subtracting 50 from each side, I get that 2s is the number 24. Therefore, s is 12. So I think our answer is that we have 10 containers of blue paint and 12 containers of silver paint. And before we move on, I do want to check that against the original problem. So I said, what was it? I said the blue is 10 and the silver is 12. So if I think about that with the original problem, I'm just going to grab my calculator here. 5 times 10 plus 2 times 12 should be 74, and it is. And for the second equation, 2 times 10 plus 3 times 12 should be 56, and it is. So, and of course I was doing that off screen with my calculator, just plugging those in and verifying that this solution, right, satisfied the equation. Alright, so again, let's move on now. That big idea right there is sometimes when you're solving a system, to do it, you need to multiply both of the equations, not just one. Okay, this item is at 1435. Let's start. It says Tracy's team was given the following system by their teacher. Okay, the instructions say solve this system. What does it say? Use the elimination to solve, and then it asks what happened. So let's come and take a look at this system. So this system, it turns out, I think I can multiply just, I guess I'll multiply the second equation by -2. So I'm thinking about getting rid of the y's. So I'm going to multiply this equation by -2. And when I do that, the top equation is still 10x plus 4y is -8. And the bottom equation is going to become -10x minus 4y equals -20. Interesting. Because when I combine those, right, over on the right hand side, it's great. It's going to be -28. But on the left hand side, you can see both my x variables are opposites and the y variables are opposites. So they're both going to go away. And I'm going to get this statement. 0 is -28. -28. What? We know that that's a contradiction. So, clearly no solution here. So why is there no solution here? Well, one of the things the text asks us to do is to take this system. Let me see what it says here. And it says, do these equations represent the same line? How can you tell? If you have not done so already, write both equations in slope-intercept form. Okay, so I'm going to take these two equations and I'm going to rewrite them in slope-intercept form. That first equation would become 4y equals -10x minus 8. And if I divide both sides by 4, it's going to become y equals -10x over 4 minus 8 over 4. And if I simplify that, y is equal to -5 halves x minus 2. So that's the top equation. The bottom equation, I can see it's the same thing already. The bottom equation is going to become 2y equals -5x plus 10. And if I divide everything, that's not exactly the same equation, is it? Because it's going to become y is equal to -5 halves x. And this becomes plus 5. Oh. So what did it say? It says, do these equations represent the same line? How can you tell? Okay. So I would say these are not the same line. They are not the same line because the way that I can tell is because they have different y-intercepts, right? One has a y-intercept at -2 and the other one has a y-intercept at +5. They do, however, have the exact same slope pattern. So in both of them, they're down 5 to the right 2, down 5 to the right 2. And if I continue playing that pattern out, what I recognize is that, I have two lines that are parallel to each other, right? Their slopes are identical, they're parallel, and they have different y-intercepts. Therefore, they'll never meet. So that's why I ended up getting this thing right here, which is clearly a contradiction, right? 0 is not the same thing as -28. So in this case, we would say, oh, these are parallel lines. There's no solution. So for part 3, or actually this should be ABC. For part C, when it says, how can you explain the solution you got in part A? I would say, oh, these are parallel lines, and parallel lines never meet. Therefore, there is no solution. So that's something that we should be looking for and be aware of the fact that if I ask you to solve a system, it's possible when you're solving the system you could get a system that has no solution. And the reason why the system has no solution is because the two lines were parallel to each other. Okay, we're starting item 4, our fourth item today at 1929, and it says the equations of two lines are given below. A table of solutions for the first equation has been started for you. Oh, that's so nice. They did start a table of solutions for me, didn't they? And one of the things that I noticed just looking at the pattern in this table is that these values increased by 2 units, right? They went up by 2, increased by 2, up by 2, up by 2, up by 2. So because the pattern is consistent on that X thing, the pattern that I observe on my outputs should be consistent also. And if you take a look at this from negative 11 to negative 6, I'm adding 5. So if you can verify that on your calculator. Negative 11 plus 5 will give you negative 6. Plus 5 will give you the negative 1 rather. And if you add 5 to that, you should be at 4. If you add 5 to that, you should be at 9. And if you add 5 to that, you should be at 14. So it's important that you observe, if you're going to use a pattern like this, observe that you really do have consistency in the change in X. And if there is a consistency in the change in X, in this case these were always going up by 2, then you can use the fact that this change is consistent to use any change that you see in the Y table to figure out new values. So these were going up by 5. So I can see my slope here should be up 5 over 2. And indeed, if I came in here and I changed this equation to 2y equals 5x plus 8, therefore y is equal to 5 halves x plus 4, you can see I can figure out the slope of that equation. One thing I noticed is that when I set this up, I placed the wrong value in, the wrong equation for the second equation. So the second equation should be y equals 5 halves x minus 2. So what I notice about this is this pattern does have it does have the same slope, and it also has a different y-intercept. So on this, let's see, I'm just going to go ahead and plug in the negative 6. Negative 6 divided by 2. So if this x is negative 6, negative 6 over 2 is negative 3, times 5 is negative 15, and negative 15 minus 2 should be negative 17, I think. Boy, why am I insecure about that? Negative 6 times, no, negative 6 divided by 2 times 5 is negative 15 minus 2. Yeah, that's fabulous. So that's starting there at negative 17. And if I go up, because these are increasing by 2, the next one should be 5 more. The next one should be at, if I go 5 more, I'm adding 5, so this should go to negative 12, right? So negative 4 divided by 2 times 5 minus 2. Yep, it is negative 12. If I add 5 to that, I would land at negative 7. I can see I kind of messed up my table next door. So the thing that I'm observing is, look, if I at negative 6, right, at negative 6, if I'm at negative 11, and over here at negative 6, I'm at negative 17. I'm at different spots at negative 6, and if I keep adding 5 as the x's increase by 2, these two lines are never going to meet each other. In fact, let's take a moment and let's look at that at Desmos now. Let's look at this graph. So we can see on this table these lines are not going to meet. So let's take a look at how this appears in Desmos. So we're going to grab this 2y minus 5x is equal to 8. Oops. There it is. 2y minus 5x is equal to 8. And the other equation, I think, let me double check, is y equals 5 halves x minus 2, 5 halves x minus 2. So when I look at these, right, they clearly have different y-intercepts, and they have identical slopes. So because of this, I can zoom out a lot, and they're going to look like they're actually touching each other if I zoom out far enough. but they're not. There's always a gap between these two. They will never touch each other, and they share no common points. And because of that, this system of equations would have no solutions. Right? So again, we're seeing this reinforced twice. If we have a system of equations in which they share the same slope, there is no solution. And even in this problem, when we look at it, as these equations were originally presented, it's not obvious, but we can change this first equation into y equals form, and we can see, that's kind of a good thing to look for. Are their slopes the same, and are their y-intercepts different? And our last item today starts at 253334. It says, and this is number 105, it says the equations of two lines are given below. A table of solutions for the first equation has been started for you, just like the last item. In fact, these two equations look pretty similar to the last two. Given what just happened, I believe that I want to solve this equation for y. So this would be negative. Let me do it. I've got a bit more room. This would become negative 4y equals negative 10x plus 8. So I just took away 10x from each side. Therefore, positive y equals, it'd be positive 10 fourths, because that's negative 10 over negative 4. And then that's going to be x. And 8 divided by negative 4 is going to be minus 2. And that 10 fourths is exactly the same thing as 5 halves x. So what's different this time around is it turns out that both of these equations are y is equal to 5x minus 2. And I already saw, because I plugged these values in below, that this is negative 17. This is negative 12. This is 7. I'm pretty sure this is negative 2 because, well, for two reasons. It's the y-intercept, and I can also see this pattern. It's negative 2. If I add 5 again, I think this is going to be at 3. So what I observe here is like, oh, this is a different beast. This time around, these two equations are identical, and any xy pair that works in one will be an xy pair that works in another. So we would say that these two lines coincide. These lines, and if you could write this down, write down the equations in this summary. These lines coincide, which means they share the same solutions. So I want to caution you, this is kind of like the situation where we're solving a system and we found out that all real numbers work. I'm being very careful here to not say all points work, because all points don't work, right? There's a select collection of points that will satisfy these equations. It turns out, though, that if a ordered pair, xy pair, satisfies the first equation, it will also satisfy the second, simply because they're the same. So don't say all real numbers, or don't say all points. It's just say, hey, these lines coincide, they share all the same solutions. As a final thing, let's go back in and look at this modified graph. It's 10x minus 4y is equal to 8. So I'm going to change this to 10x, 10, what was it, 10y? No, this was 10x minus 4y. So 10x minus 4y. Let me get rid of this thing. 10x minus 4y is equal to 8. And when I do that, what I observe is like, oh, look at this. These are now the same line. And if an ordered pair is a solution for one, it's a solution for both. You can see there's some nice solutions here. We know that negative 2 was the y-intercept. And every single time the slope was 5 halves, if I go up 1, 2, 3, 4, 5, and then over 2, here's another pair of integers that they share, right? The point, what is that? It's the point 1 comma. Oh, 1/1/2, huh? I guess so. So that is it for today. We're at 30 minutes. I hope you have a great day. Thank you for your careful attention and following this along. Again, I'll be online this afternoon as always. If you have any questions about today's talk or your assignment, please stop in. This is Roberts. I look forward to seeing you again soon.